good afternoon. My name is Mr. Royce. I'll be your AP Statistics instructor today. We're going to start out by singing happy birthday to Bethany and Caleb. So everyone, whole class, come on up in front of the camera. Now, yes, everyone, come on up. Make sure you can be seen on YouTube. No. Well, okay, that's a good idea. Bethany and Caleb, come on up. Here's what we're going to do. Bethany and Caleb. Now, this is in keeping with the long tradition of singing a happy birthday in monotone whenever you're in math class. So, oh, Caleb, we can't see you. So we'll go in monotone. Yeah, phones away. Thank you so much, Josh, for reading your phone. It'll be happy birthday in monotone, Bethany and Caleb. Ladies first. Here we go. Ready? Go. Happy birthday to you. Happy birthday to you. Everyone. Happy birthday, Bethany and Caleb. Happy birthday to you. Let's give them a hand.
Good job.
Birthday. So what are you, 18?
18.
Wow.
You can officially vote in last week's election.
Well, you could have voted if you're 17
I know.
in those.
Really?
I did. I didn't know that until now. You could in 17 in those.
We're starting chapter 23 today.
Oh,
How many
that was
units have
very
we had?
interesting.
This is unit 10. There's 11 units in this course. And today we're beginning unit 10. It's a 3-chapter unit. That's chapters 22, 23, 24, 25. So we're starting chapter 23 today, T models. So let's take a look at the big picture. What's going on with T models? The models of sampling distributions that we've seen so far have been not many in number. So far, what we've seen as far as models go, or we've seen normal models. Normal models require 2 parameters, a mean and a standard deviation. We have seen binomial models that require 2 parameters, fixed number of successes, n and p are the 2 parameters in the binomial model. We've seen the geometric model, which requires only 1 parameter. So we've really only had 3 models so far. Today we get our 4th model. Sometimes you say according to the normal model, according to the binomial model, according to the geometric model. Today's going to be according to the student's T model. It's the T model, lowercase t, and the parameters that you need are, first of all, you need number of degrees of freedom, so sub df, and you're going to need a mean, mu, and a standard deviation, sigma. So it's really 3 parameters, a mean, a standard deviation, and a number of degrees of freedom. So let's talk about T models and why on earth we use them. We just finished up a unit where we were using the normal model, which can be thought of as a Z model, because if we rotate this, notice how when you rotate an N, it turns into a Z, where Z is the Z-squared number of standard deviations. So you could think of it as a Z model, but it's the normal model, is the way we call it. The T model is named after William Gossett. And William Gossett is a mathematician who worked at a beer company in Dublin, Ireland, the Guinness Beer Company. Now, this is Wheaton Academy, not a lot of beer drinking going on in the halls. But at other high schools, you just never know. You never know what's going on. There's a lot of beer drinking in the history of statistics because William Gossett's job was to taste the beer and measure its quality. But because Gossett wanted to keep alert during his job, he wanted to keep the sample size small. Thank you. So, how do you keep the sample size small? Well, instead of him drinking 2 or 3 samples, and keep in mind there's a lot at stake, because if the beer is bad, and these are vats of beer that are like the size of this room. I need a pass. You know what I'm going to do? I'm just going to hit pause. we're back. So imagine a vat of beer that's the size of this room. The null hypothesis is that it's good beer. Then you take some samples. You're not supposed to drink the entire vat of beer. You're supposed to sample it. And then maybe stir it up, take 3 or 4, maybe 5 samples. N equals 5 would be the sample size. Take the average of the ratings. What if you decide it's bad beer? You have to dump the entire vat into the ocean. This is Dublin, Ireland, a little bit south of where the Titanic was manufactured, Belfast, Northern Ireland. So we'll see ya. Take care, have a good break. So we have, it's one of those situations in which, what if you incorrectly reject the null hypothesis? Null hypothesis is that it's good beer. Alternate hypothesis, not good beer. So the consequences, and this is an emotional impact here. Can you imagine draining an entire vat of beer the size of this room into the ocean and it was incorrect? You made a type 1 error. Now you know the emotional impact of a type 1 error. A type 2 error would be selling bad beer. You're keeping beer that should have been dumped. So both errors are severe. But Gossett was making too many type 1 errors. He was rejecting. Now, what they actually did was they sent it for further testing. He said, I reject the null hypothesis. There's sufficient evidence to reject the null hypothesis. It turned out it wasn't really bad beer at all. So he needed to come up with a new model. And he came up with a T model, which is just like a normal model, but in a normal model N, you want to turn a normal model into a T model, you need more area in the tails. So a T model looks just like a bell curve. It is a bell curve, except it's more spread out. And so basically, you have to have really, really bad values. You want the rejection region to be 5%. On a normal model, 5% of the area is here. So if your observation is to the right of this value, although we're rejecting bad beer, so suppose we have, it's just left tail. So suppose we get in something that's a certain number of standard deviations below the mean, maybe like 3 standard deviations below the mean. That's not very far off of average. This is what Gossett was doing. He was getting beer that was a little bit low in quality, but turned out that it wasn't really bad after all. So in a T model, you're going to have more area in the tails, so that if you want the worst 5% down here, it's farther away. You have to go farther away. It has to be really bad beer compared to a normal model, which it's less spread out. And notice that here is the 5% rejection region. Notice it has to be really bad on the green curve to be rejected. This is what happens with small sample sizes. The Guinness Beer Company didn't like the fact that one of their employees made an important mathematical discovery, so they didn't let him name the model after himself. They said, the only way we're going to let you publish is if you use a pseudonym. We're not going to let you go out there with your real name, because then people will think that in order to drink beer, you've got to be good at math. Can't have that. So instead, he had to call it the Student's T model, or the T model for short. It should be called the Gossett model, because William Gossett of the Guinness Beer Company came up with it in the first place. You need not only a mean and standard deviation, but you also need a number of degrees of freedom. Where basically the number of degrees of freedom is sample size minus 1. So here's the first big formula for today. The number of degrees of freedom is sample size minus 1. And the limit as degrees of freedom, in fact, this is the big idea here. The limit as n approaches infinity of the T model with a certain number of degrees of freedom, d sub f, equals the normal model. So As the sample size goes to infinity, the T model turns into a normal model. So check this out. If the degrees of freedom is like 3, then you might get this really flattened bell curve. But if it's 4, 5, 6, maybe it's, degrees of freedom is, 90. Now the green T model is getting even closer to a normal model. If the degrees of freedom is 1,000, then the T model is going to be almost indistinguishable from a normal model. So T models are used for small sample sizes, and they're used whenever we care about the true mean, mu, the true mean, instead of the true proportion. So Z is for proportions, T is for means, always. So take out your AB80 chart. Let's fill in row 3 of your AB80 chart, because chapter 23 is about row 3 of the AB80 chart. Here we go. Let's do this. Notice the T model, instead of a Z score, you're going to get a T score. Now, friends, T and Z function in the same way, in that they tell you the number of standard deviations you are from the mean. And look at how the formula for T has the same structure as the formula for Z. So instead of P hat minus P sub 0, this is right next to the 2 in AB80, 56, 24. Here's the 2 in 24. Instead of Z equals P hat minus P sub 0, it's T equals X bar minus mu sub 0. You see, T is for means, Z is for proportions. So when I say go, I'd like all of you to say out loud and in unison, Z is for proportions, T is for means, always. Ready? Go. Z is for proportions, T is for means, always. Okay, so what's the standard deviation? Yogurt Day helps us understand why it's sample standard deviation S over the square root of n. That's not sigma, friends. We don't have mu and sigma. We have X bar and S. X bar instead of mu. In fact, when William Gossett would test beer, he would take maybe a small sample size, n equals 5. He would average the quality ratings, like, oh, how would you rate that sample? I'll give it a 7. How about this sample? I'll give it a 7.5. I'll give that sample a 3, a 9. It's a 10. He would average those 5 quality ratings to get X bar, and then he would calculate S as sample standard deviation. Using X bar and S, he could calculate this because n might be 5 if the sample size is 5, and the hypothesized mean is mu sub 0. So, filling in row 3 of the AB80 chart, it's called the one sample t-test for means. The null hypothesis is that the beer is good. Alternate hypothesis, beer is not good. By the way, a mu trap, if you want to build a mu trap, how many traps have we had? We've got P traps, D traps for the difference between two proportions, and now for a mu trap. To build a mu trap, you take the sample mean, so we can get a 95% confidence interval for the true average quality rating of this vat of beer. So instead of P hat plus or minus Z star, it's X bar plus or minus T star sub n minus 1, where the number of degrees of freedom is, you already know it, degrees of freedom is n minus 1 times S over the square root of n. This is standard deviation. So it has the same structure as a P trap. This is a mu trap. It's called a one sample T interval for means, and you can build a mu trap by running the stat test 8. That's putting AB80, it's putting the 8 in AB80, 56, 24. As far as conditions to complete row 3, the conditions are independence assumption, randomization condition, or representative sample. You've seen that before. Now, here's an acronym. It's a new acronym. So fill this one in on the back of your paper. Fill in the following acronyms. NPA is the normal population assumption. You have to assume that the samples of beer quality are normally distributed. And NNC, so that's normal population assumption. For NNC, that's the nearly normal condition, where the key numbers are 15 and 40. So 15 and 40 are the boundaries between small sample size, medium sample size, and big sample size. It's different than more or less than 30. If the number of samples is less than 15, that's called a small sample size. 15 to 40 is medium sample size, and any sample size greater than 40 is large sample size. Those are rules of thumb there. Okay, so those are the conditions for building a mu trap or running a one sample t-test. So, one sample t-test for means. That's row 3. So today's lesson is all about row 3. Let's go back to the handout. By the way, yeah, chapter 24, just so you know what's going on in this chapter, may as well mark this down. Now's as good a time as any. So this is chapter 23 is row 3. Chapter 24 is row 4 of the chart, which we haven't filled in yet. And chapter 25 is row 7 of the chart. So yeah, difference of means, mean of differences. So this unit is chapters 23, 24, and 25. Chapters 26 and 27, these two are chapter 26 of the book, and the last chapter of the school year is the last row, chapter 27. So that's how we're going to finish up the course. Now back to the lesson. Notice that when you're building a mu trap, you need T-star. So the T-star sub n minus 1 is what we need to learn how to do next. It's called the critical T-value, and that's what they ask for in problem 1. What's a critical value of T? When they ask you for a critical value of T, they're asking for a T-star. And you know how when we found Z-star, we always used which command on the calculator? It was inverse normal. So pull out the calculator. There should be an inverse T command on your calculator. That works just like, so it's like inverse Z. They call it inverse normal, but it's really inverse Z to get Z star. Even though they call it inverse normal, normal is like Z. Now, we're going to do inverse T. Some of the old school calculators don't have inverse T on it. So I have a program in case your calculator doesn't have it, but it looks like these days all the calculators are pretty updated looking. Let's take a peek at what happens when you go to the distribution menu. I have inverse T on mine, it's item 4, it's right under inverse normal. Raise your hand if you have the inverse T command on your calculator. And Josh, do you have it?
It's dead.
Oh no!
I forgot I didn't charge it yesterday. Yeah.
It's dead. How long has it been dead?
Since yesterday, so.
Oh, so it doesn't smell too bad. I'm trading the phone.
Calculator.
Oh, calculator?
Yeah.
Oh, whatever.
That's better. I mean, it is.
But it's that.
It's dead. All right, inverse T. So item 4. Let's go to item 4. Let's see how this. Oh, wrong environment. So on the home screen, are we still recording? Yes, we're still recording. So inverse T. We go to the distribution menu, pick up item 4. Now, here's what they're telling you. They're telling you a 90% confidence interval. So it's still the left area idea. If this were inverse, if we were finding a Z star, we'd do inverse normal of 0.95. Here, we need 2 arguments. Not only do we need the left area, which is 0.95, but we also need to feed it the number of degrees of freedom, which are given as 17. So 1.739 is the answer to first problem we had. So right, T star, but it's not just any old T star, it's T star sub 17 equals 1.379. And just to confirm, the calculator screen that we should be looking at to get that is one that looks like this. It says inverse t of 0.95, comma 17. Any questions on how to use the inverse t command to get a t star sub 17 value of that? I'm going to red box the final answer. Amelia, go ahead.
Why is it 1.95?
Oh, well, here I'll draw the picture. So 0.95, it says a 90% confidence interval. So we've got, this is the curve t sub 17. Has a mean and standard deviation with the number of degrees of freedom is 17. So 90% of the area is between negative t star and positive t star sub 17. So inverse t requires left area, just like inverse normal requires left area. And if 90% is between the t stars, or between t star and negative t star, then the other 10% is split, 5% in each tail. So here's t star sub 17. How much area is to the left of t star sub 17? The answer is 0.90 plus 0.05 or 0.95. Does that answer your question to your satisfaction? All right, so now try letter B on your own. 88 degrees of freedom. Go ahead and power up the calculator. Try part B. Hopefully you typed in 0.99, 88. That's all there is to that one. Oops. Okay, so inverse t of 0.99, 88 degrees of freedom. There's our t star. Use a t star just like you use a z star for building a mu trap, 2.369. Any questions on part B? All right, now part C says, oh, no further looking. Okay. Find the p-value for t is greater than 2.09. Let's draw a picture for this. Let's draw a t distribution. Instead of a z distribution, it's a distribution of t-scores. This is t sub 4, and we're just going to put the mean at 0. It's a standard t distribution with a mean at 0 and 4 degrees of freedom. Okay, t is greater than 2.09. So here's 2.09. The p-value would be the area under that curve. So, but instead, it's not a normal model, it's a t model. So instead of normal CDF, we're going to use t-CDF. I don't even know if you knew there was a t-CDF, but you'll find it on your calculator. Go to t is for means. T is for means. So see if I can find a t-CDF. Oh, found it. It's item 6. T-CDF on the home screen. And it works just like normal CDF. We need to give it the low and the high. So it's 2.09, comma 999, comma degrees of freedom, which is 4. And that will make the adjustment for the small sample size. In fact, notice how that compares to normal CDF. Normal CDF of 2.09, comma 999. Before you press enter, let's think about this. Is this going to be a bigger number or a smaller number based on what you know about these things? Raise your hand if you're thinking this p-value will be greater than 0.0524. Raise your hand if you think it'll be less than 0.0524. Some say less. Raise your hand if you're just not sure how to think about it. Not sure how to think about it. Look, here's how to think about it. Compare a t model, which I'm putting here in green, with a normal model. The normal model, remember, is less spread out. And so if you took, the same, like a z-score of 2.09, would you expect the blue area to be greater or less than the green area? Class, greater or less? If you think it's greater, if you think the blue area is greater than the green area based on this picture I drew, hold up one finger, that's 1 for greater. If you think blue is less than green, hold up 2 fingers. I'm seeing people holding up I've seen some people holding up a number of fingers that's oscillating between 1 and 2. Some are holding up 2. It looks like it's less area. Remember, the T models have fatter tails, and so they're going to have more area. The Z models, the normal models, have skinnier tails. They're going to have less area, so it should be a smaller number. Let's find out. Sure enough, it's wow, it's a lot smaller. It's a lot smaller. So notice that this makes sense. Gossett would not reject the null hypothesis if he's 2.09 standard deviations above the mean on the T model. But if this were a normal model, he would totally be rejecting the null hypothesis. See, this is what protected him from ditching too much beer. It's like the p-values were not as small because of the increased area in the tails. All right, so there's a lot of history behind statistics. Then this last one, we've got absolute value of t is greater than, what am I doing? I've been teaching calculus for too long. I put in a vertical axis there. It's only a horizontal axis. The absolute value means we got 1.78 into the right, or it could be negative 1.78 into the left. So let's find this right area on the t sub 22 distribution and multiply it by 2. Just find this thing with 22 degrees of freedom, multiply it by 2. That should be the answer to letter D. So I'll give you some time to do the calculator work. 1.78. Who took my calculator? There's my calculator. Okay. Absolute value means you have to multiply it by 2, 1.78, comma 999. And how many degrees of freedom? Yeah, 999 is close enough to infinity. 22 degrees of freedom. Okay. That, something terrible went, I'm using numbers here. I should be using TCDF. So TCDF is item 6. So we're going from 1.78 to 999 with 17 degrees of freedom. I think, let me see if I'm, no, 22 degrees of freedom. So overstrike that with 2. Hopefully you got for an answer 0.0444. Times 2 gives you 0.0888, or 0.089. Any questions on how to get a p-value? The area of these two curves is 0.0889. Just arrow to both tails. 0.0889 is the area of both tails combined. Caleb.
What is the degree of freedom? Like, why do we do 1 or n minus 1?
Yeah, so the question is, why do we use n minus 1? One way to explain degrees of freedom is, suppose you want to get 4 numbers that average 10. And suppose I give you the first 3 numbers, 14, 20, 80, and something else, and I want the average to be 10. Well, it doesn't matter what these first 3 numbers are, because I do have 1 degree of freedom here. I can solve for that third number when I add the numbers up and divide by 4 to get 10. So when I have 4 numbers, I have really 1 degree of freedom. So I can have 3 of the 4 numbers be determined, no freedom, and as long as I have that 1 degree of freedom, I can ensure that the average is going to be 10. So that's an example of how degrees of freedom is used in mathematics. Now, in terms of the degrees of freedom concept in the T model, that is reserved for a future course in statistics. I'm just giving you the rough idea of what we mean by degree of freedom. If you're going to average 4 numbers and make sure that it's 10, you really have just 1 degree of freedom. I'm sorry, you have 3 degrees of freedom. You have 3, in that you can freely choose any 3 numbers. So when you have 4 numbers, the degrees of freedom is 4 minus 1. Just to illustrate that further, since I didn't explain that perfectly, how many degrees of freedom do you have if you want the average of 8 numbers to be 40? Well, you can freely choose 7 of those numbers. You can say 1, 3, 100, 3, 4, 5, 6, 7. But the 8th number is then determined. You have 7 degrees of freedom, but you're going to add up those 8 numbers and divide by 8 to get 40. 7 free choices. So you have 7 degrees of freedom in this problem. The 8th one is then determined by your first few choices. So that's an example of the degrees of freedom concept. But beyond that, it sounds like you're the sort of person who would want to take additional courses in statistics anyway, aren't you? That's what I thought. See? Now it's on YouTube, so it's official. So here we go. Let's go to next, number 9, pulse rates. Now that you're 18, you can make decisions like that. I'm going to study statistics. No, you still got to honor your parents. Don't ignore what your parents say. Parents are important. This is Parent Week here at Wheaton Academy. We're going to have a little sermon on parents in chapel on Monday. Here we go. Let's take a look at some mu traps. So here we go. Pulse rates. A medical researcher measured the pulse rates, that is beats per minute, of a sample of randomly selected adults and found the following. Students T don't cooperate with the system. Guinness isn't in charge. It's the Gosset's T model, everyone. I can't believe they didn't have the courage to let people know that there's mathematicians who work at the Guinness Beer Company. That's disturbing to me. With 95% confidence, there it is. So, this is the mean. We're trying to capture the true mean pulse rate, 70 to 74. When during the cross-country season, my mean pulse rate was under 60 beats per minute. I was at 59. I went for a doctor's appointment. I was at 59 beats per minute. My doctor asked me, "Are you a runner?" Because most adults have resting heart rates between 60 and 90, and he wasn't sure whether to be concerned about me. I said, "Oh, it's okay. I coach cross country. It's okay for my resting heart rate to be low." But here's a 95% confidence interval for the true mean resting pulse rate it's probably for Americans. So we're 95% confident that, explain carefully. So it's bots. Based on the sample, we're 95% confident that the mean beats per minute, it's probably for Americans, for American adults at rest, is between 70.887 and 74.497. That's wrong. It's got to have units, beats per minute. So BPM. What is the margin of error for this interval? Well, it's just half of the diameter. The margin of error, it's just going to be, the blueprint for building this thing is x bar plus or minus ME, the margin of error. Just like the blueprint for building a p-trap was p hat plus or minus ME. So just subtract and divide by 2. The margin of error is take the tooth on the right minus the tooth on the left and divide it by 2. So the margin of error is half the width for about 1.8 beats per minute. Any questions on that one? Don't try that with a $300 stylus at home without all of the adult supervision you crave. Oh, that's right, some of you are adults. Part C. Hello. Clear annotations. Let's see what that does. Yes, those are still there. If the researcher had calculated a 99% confidence interval with the margin, we already know this, we learned this concept, the larger the confidence interval, the higher the probability the interval contains the true mean. So would the margin be larger or smaller? Yeah. Anyway, larger is the answer. And then, that's it for that page. Page 2. Done with page 2 already? Are you kidding me? By the way, since I wrote ME on the board, I want you to have the formula here. The margin of error formula for p-traps was z star times the standard error of the sampling distribution of p hat. Z is for proportions. T is for mean. So margin of error for a mu trap is t star sub n minus 1 times the standard error, which is an approximation of the standard deviation of the sampling distribution of x bar. So instead of it being SE of p hat, it's SE of x bar. So that's the actual new formula for margin of error when it comes to building mu traps. And would the margin of error be larger or smaller? Okay, larger, no big deal there. Now, this is, next, I actually want to go to the last page. So let's go to page 14, problem 14, parking. This is a good one. Good one for you to be doing. What assumptions must you make in order to use these statistics for inference? And in terms of note-taking, wow, look at that. That looks pretty impossible to read. Wouldn't you agree? All right. Yeah. Well, this is actually a good example to go through when the rest of the crew gets back. So, I mean, it's not like there's any homework over break anyway. Now, if you want to over break, how many of you are thinking, man, do I need a break? I'm thinking of doing as little homework as possible over break. How many of you are like, come on, we got an AP test coming up. You got to give us some homework to do over break. No one? Okay. You know what? I think you should take a break. You work hard. So, no homework over break. Relax, and we'll see you Tuesday. Have a good night.